Welcome to tutorial number 9. In this tutorial we're going to be discussing inductors and inductance. You can test yourself on your understanding of this tutorial with drill number 6. On the left hand side of the screen we've got the symbols for an inductor. An inductor is basically a conductor coiled into a coil, and often a magnetic core is inserted into the inductor to increase its inductance. So on the left hand side you have an air core. The symbol has nothing else except the inductor symbol showing cores of wire. The one next to that is an iron core inductor. That's a laminated iron core because two lines. Iron core inductors are only used at low frequencies, 50 Hertz, transformers, and at audio frequencies. On the bottom left you see the symbol for a ferrite core inductor. Ferrite is a material which concentrates magnetic lines of force, just like iron. The difference is that the losses in ferrite are less than what they are in iron. As the frequency goes up, currents are induced into the core, which causes heating of the core. And with laminated iron cores, once the frequency goes above about 100 kilohertz, the losses are too great, and so we switch to a ferrite core or an air core. Ferrite is good up to VHF. On the bottom right we've got a variable inductor, and on the left we've got a pictorial view of what an inductor looks like. Coil of wire, sometimes wound around a magnetic material, sometimes just an air core. Air has a permeability of 1. Permeability is the ability of a material to concentrate magnetic lines of force. Air has a permeability of 1. Inductance is directly proportional to the permeability of the core. So if we replaced air with a material with a permeability of 10, then that would increase the inductance of the inductor by a factor of 10. The other things that affect the inductance of an inductor are the number of turns. The more turns, the more inductance we have. Size of wire does not significantly affect the inductance. It's all about the number of turns of the inductor and the diameter of those turns. The greater the diameter of the inductor, the more inductance it has. If you had 20 turns on a 10 millimeter ferrite core and you used the same ferrite core and put 100 turns rather than 20 on it, you would have 5 times the amount of inductance. Inductance is directly proportional to the number of turns on the inductor. The other thing that affects inductance is the spacing of the turns. If they're more broadly spaced, the inductance is lower. If they're more closely spaced, the inductance is higher. Inductance is all about current. Capacitance is all about voltage. Just to remind you, capacitance is the opposition to changes in voltage. A capacitance is able to oppose changes of voltage because as the capacitor charges to the supply voltage, it pushes back against the supply voltage, inhibiting further charge of the capacitor until eventually the capacitor is fully charged and it has the same voltage as the supply and pushes back as hard as the supply is pushing forward and will not charge anymore. On the other hand, inductors are all about current. The unit of inductance is the Henry, and a Henry is defined as if you have got an inductor and the rate of change of current through that inductor is 1 ampere per second. That's how quickly we're trying to change the current. So the rate of change of current is 1 ampere per second. If that produces a voltage across the inductor of 1 volt, then that inductance is 1 Henry. The reason why the inductor gets a voltage across it is because when we try to make a current flow through an inductor, the inductor gets a magnetic field around it, and that magnetic field is changing because the current is changing. If the rate of change of current is 1 ampere per second and that produces a voltage across the inductor of 1 volt, the inductance is 1 Henry. The reason why the inductor produces a voltage across itself and in effect acts like a source of EMF is because of Faraday's law. When relative motion exists between a conductor and a magnetic field, an EMF or voltage is induced into the conductor. So when we try to create a current through an inductor, the inductor itself, because of its expanding magnetic field, produces a voltage across itself, Faraday's law, and the polarity of that voltage will oppose the current that produced it. That's called Lenz's law. You don't have to know that one. What you do need to understand, but you won't be assessed on, is what inductance is. Inductance is the electrical property of an inductor which opposes changes of current through it, just like a capacitor did. A capacitor had an opposition to change. That opposition was to a change in voltage, and that opposition was equal to XC equals 1 over 2 pi FC. With an inductor, the opposition is to changes of current, not voltage. And that opposition is called inductive reactance, and XL equals 2 pi FL. We'll be talking a lot more about that, and we'll also be talking about how you can work out the total inductance of inductors in series and in parallel for your standard amateur radio assessment. If you try and increase the current through an inductor, the current doesn't increase the way it would through a resistor. With a resistor, there is no induced voltage across the resistor due to Faraday's law. With an inductor, there is. When you try and change the current through an inductor, the magnetic field expands. Let's suppose you're trying to increase the current. Well, then the magnetic field is expanding. You have relative motion between a magnetic field and a conductor, so an EMF is induced into the conductor, in this case a inductor. And the polarity of that voltage will oppose the current that produced it. In the diagram, the current is flowing from left to right, from negative to positive, like it always does. The voltage induced across the inductor will be negative on this end, on the left-hand end, and positive on the right-hand end, but that will try and create a current in an anti-clockwise direction against the direction of the current that's producing it. It won't succeed in producing a current because the main current is going from negative to positive from the supply. But what it will do is slow down the build-up of that current. So when you apply a power supply or a battery to an inductor, the current doesn't reach maximum immediately. The reason being is because the inductor removes energy from the circuit and stores it in its magnetic field. So there is a delay in the current reaching its final value. Suppose the current is not changing. Suppose it's steady. Well, then the magnetic field is steady and there's no induced voltage across the inductor. Suppose now we try to decrease that current. If we try to decrease the current, the magnetic field will collapse, energy will come out of the magnetic field, and a voltage will be induced into the inductor, opposing the change we're trying to make. So if we're trying to decrease the circuit current, the reducing magnetic field will induce a voltage which will try and maintain the status quo of the current in the circuit. So with inductors, there is always this delay in current. If we try to increase current, yeah, we can increase it, but it will take a little while before it happens because the inductance will absorb energy. If we try to decrease the current, yes, we can, but it'll take a while to decrease the current because as we're trying to decrease it, energy is coming out of the magnetic field and into the circuit to maintain the status quo of the current. That's what inductance is. Just once more in summary, capacitance is that electrical property of a circuit which opposes changes of voltage. Inductance is that electrical property of a circuit which opposes changes of current. That opposition for capacitance is called capacitive reactance, and Xc equals 1 over 2 pi Fc. And that opposition for inductance is called inductive reactance, and XL, inductive reactance, equals 2 pi FL. When we put inductors in series, like we have here, 3 150 microhenry inductors, what we are in effect doing is adding more turns to the inductor by seriesing them up. The total inductance then is going to be greater, and it's simply going to be the sum of the individual inductors, exactly the same way as you find out the total resistance of resistors in series by adding them together. I'll do that for you just to remind you. RT for series circuits, so this is resistance for series circuits, equals R1 plus R2 plus R3, etc., depending on how many R's we have. For inductors, it's the same thing when they're in series. LT, and I'll put series just to remind you, and you've got the circuit there, equals L1 plus L2 plus L3, etc., depending on how many L's you have. And in the above circuit, that would give us a total inductance of 450 microhenries. Treat inductors in series exactly as you would resistors in series. When you put inductors in parallel, the total inductance is decreased. Here we've got two 50 millihenry inductors in parallel, and I know that the inductance between A and B is going to be less than 50 millihenries at a glance, because in parallel inductive circuits the total inductance is always less than the lowest inductor value. So if you had a 10 millihenry in parallel with 5 100 millihenry inductors, you know instantaneously that the total inductance of that circuit is going to be less than the lowest inductor, which in this case is 10 millihenries. So the total inductance of a 10 millihenry inductor with a multitude of 100 million inductors in parallel, the total inductance is going to be less than 10 millihenries. Now, for the standard exam, you're always going to be given inductors in parallel of the same value. And if you recall how you treated capacitors in series, with capacitors in series, you took the value, and they're all the same value. You took the value of one capacitor in series and divided it by the number of capacitors that there were. You do exactly the same thing with inductors. With inductors of the same size in parallel, you take the value of one inductor and divide it by the number of inductors. So this is the easy method. LT for a parallel circuit, and they must be all the same for this to work, is the value of one inductor, and since they're all the same, it can be any one, divided by the number of inductors. So in the example above, the value of one inductor is 50. We divide that by the number of inductors, which is 2, and so the total inductance of that circuit is 25, not micro, millihenries. Very easy. The formula that works for inductors in parallel when they're not the same size is on the screen. LT is the reciprocal of the sum of the reciprocals of the individual inductors. You will not have to do that in your standard assessment. They will always be the same value, and you can use them like I just explained to you. But let's have a look at using the equation that always works in all circumstances for inductors in parallel. LT equals the reciprocal of the sum of the reciprocals of the individual inductors. So in this case, this L1 would be 50. Now we don't have to put millihenries into the calculator because they're both in millihenries. If you had an inductor in microhenries and another one in millihenries, you would have to put them into the calculator as microhenries and millihenries using the exponent function on the calculator. But when they're all milli or micro or nano or pico, you don't have to worry about the unit because you can add apples to apples. Alright, let me bring up the calculator and work out. We know the total inductance of this circuit is 25 millihenries, but let's prove that using the equation. All clear? Always hit all clear on your calculator because you may have a remaining calculation from a previous calculation. So we're going to enter 50, and we need to find its reciprocal by dividing it into 1. I press the reciprocal key, 1 over x, plus, the next one is 50, could be 70, 80, this works for them all, 50, reciprocal, equals, so the 0.04 is the sum of these two reciprocals. The answer is the final reciprocal. We've got to divide our denominator into 1, which is a numerator. Let's hit that, and we better get 25, otherwise I'm going to be quite embarrassed. And we get 25. There you go. That's how to do it so that it always works. But for your standard assessment, it'll be the method that I showed you earlier. Divide the value of one inductor by the number of inductors there are, the only proviso being is that all of the inductors must be the same value. Just as capacitance or capacitive reactance can oppose the current flow in a circuit by opposing changes of voltage, inductance can oppose the current flow by opposing changes of current. That opposition that an inductor has to current flow is called inductive reactance, and the formula is XL equals 2 pi FL. You should remember that. You will not have to use the equation, but you will be asked questions about how the inductive reactance changes with either frequency or inductance. And as you can see, there's no denominator or numerator, so 2 pi FL is just a numerator. So XL is directly proportional to F and L. So whatever F does, XL does. So if FL increases, XL increases. If F decreases, XL decreases. If L increases, XL increases. If L decreases, XL decreases. That's called a direct proportion. Now you won't have to do something like this, but I'm going to show you how to work out how much current is flowing in the circuit on the screen at the moment. In order to work out how much current is flowing, we need to use the Ohm's law equation. I equals, we normally say E over R, but we have no R. We have only got inductive reactance, XL. XL is an opposition like R. The only difference between XL and XC and R is that R dissipates heat, produces heat, whereas inductive and capacitive reactance do not dissipate heat. Both capacitors and inductors take energy from the circuit and to return that same energy to the circuit on the second half cycle. So in order to find out how much current's flowing in this circuit, we need to work out the inductive reactance of the circuit. You will not have to do that. And that's 2 pi, I need pi, there we are, multiplied by the frequency, which is 1000 Hertz, 1 kilohertz is 1000 Hertz, by the inductance, which is 1 Henry, equals. Now, 2 pi is roughly 6. It's a good idea to remember that. Pi is roughly 3. It's 3 1/7. So no one's going to worry about... you're going to get the right answer in the exam if you just take pi as 3 and you take 2 pi as 6. So that becomes, as an approximation, 6 times 1000 times 1 equals 6,000 ohms. And that's XL, that's inductive reactance, it's not resistance. Now that we know the inductive reactance and we know the applied voltage, we can use the equation I equals E over XL equals E is 10 and XL is 6,000 equals. Right. Let's bring up our calculator. Okay. We're solving this problem here. We've already worked out the inductive reactance is 6,000 ohms, so we're using I equals E over XL to work out the current that would be shown by the ammeter. Let's bring up the calculator and we're going to divide 10 by 6,000. 10 volts divided by 6,000 ohms of inductive reactance equals 1.666 repeating exponent 3. That exponent 3 minus 3 is milli. That means milli. E minus 3 means milli, E minus 6 means micro, E minus 9 means nano, E minus 12 means pico. So the current flowing in this circuit is 1.66 recurring, and it's milliamperes. You won't have to do that. I just wanted to show you how inductance controls the circuit current. What I'd like to show you is how inductive and capacitive reactance change with frequency. If you look at this equation, XL equals 2 pi FL, that's a direct proportion. If F increases, XL is going to increase. On these axes, we've got frequency on the horizontal axis and the reactance on the vertical axes, and the green line is the inductive reactance. So as the frequency is increasing, to the right, the inductive reactance goes up and up and up and up and up and up. If you double the frequency, you double the inductive reactance. Because capacitive reactance is inversely proportional to frequency. As the frequency goes up, the capacitive reactance shown in blue goes down. So as the frequency is rising, the capacitive reactance goes down, and with inductive reactance, as the frequency rises, the inductive reactance goes up. An interesting thing happens at a certain frequency where they're both the same reactance. That's important if you ever do your advanced license, because that frequency there, where the two reactances are equal, is called resonance. What we're going to do now is go through section 6 of sample questions.doc in your document folder of your DVD or CD, and we're going to go through some sample questions on inductance and things related to inductance that you could possibly get in the standard amateur radio assessment. Question 6.1 asks for, a pretty easy one, it's asking for what is the unit of inductance. Well, the unit of inductance is the Henry, named after Joseph Henry, and the capacitance is the farad, of course, is the unit of capacitance. Just to help you remember these, the watt is the unit of power, and the ohm is the unit of resistance. Just remember there is a property called inductive reactance, and that equals 2 pi FL, excuse my lazy pi, and it is also measured in ohms. But ohms of inductive reactance are not like ohms of resistance, because ohms of inductive reactance do not dissipate heat. If you connected an inductor or capacitor to your power point, and you would never do that, but if you did and it drew current, your power meter would never measure that you're consuming any current, because even though you're drawing current, you're not consuming current, because inductors and capacitors take energy from the supply and always return it to the supply. So 6.1, the unit of inductance is the Henry, after Joseph Henry. Question 6.2, the presence of an iron core in an inductance. Well, if you want to increase the inductor, you need to put a core in it. And if you put a core that's of magnetic material, and iron is a magnetic material, it has a permeability greater than air. Air has a permeability of 1. So putting any core into an inductor with a permeability greater than air will concentrate the magnetic lines of force and increase the inductance of the inductor in direct proportion. So if we had an air core and the inductance was 1 Henry, and we replaced the air core with a permeability of 10, that would increase the inductance by a factor of 10, making it 10 Henrys. Question 6.3, the inductance of a coil would be increased by increasing the spacing between the turns. No, that would decrease the inductance. Removing some turns, that would decrease the inductance. Increasing a brass core. Well, brass has a permeability, is not a magnetic material. It has a permeability of less than 1. It does not concentrate magnetic lines of force. So that C would not be the correct answer. Inserting a ferrite core in the inductor. Ferrite has a high permeability, and that would increase the inductance of the inductor. The inductance of a core would be increased by inserting a ferrite core in the inductor. That would increase the inductance, that would increase the inductive reactance, and that would reduce the circuit current. Question 6.4, if the frequency of the AC supply is increased, the current through the inductor will. Now I've put the equation for inductive reactance in here to help you. In your exam you will not get it in the question, however you will get this equation on the formula sheet that's given to you during the assessment. And this equation tells us that inductive reactance is directly proportional to F and L. So whatever F and L do, that's what inductive reactance does. So let's have a look at the question again. If the frequency of the AC supply is increased, so F is increasing, the current through the inductor will decrease. Now the reason why the current through the inductor will decrease is because we've increased the frequency. If you increase F, that increases XL. And XL is an opposition. So if you increase F, that increases XL, and I equals E over XL. So that means that the circuit current, because they're asking us about current here, will decrease. Question 6.5. The purpose of the inductive reactance of the inductors in this filter circuit is to. Now I'll tell you what the filter is in a moment, but we don't need to know this to answer the question. We will be talking about filters later on. The purpose of the inductors in series is so that their inductive reactance can suppress high frequencies, and the reason being is that for low frequencies, using the equation XL equals 2 pi FL, for low Fs the inductive reactance will be low. For high Fs, high frequencies, the inductive reactance will be high, and that will stop the passage of high frequencies through this filter. It's a low pass filter, by the way. So it passes the inductive reactances, oh, that's the wrong one, passes the low frequencies and suppresses the high frequencies, because the inductive reactance of these inductors is high for high frequencies, stopping them, and low for low frequencies, allowing them passage through the filter with barely any attenuation at all. Question 6.6, and again I've put the equation in to help you. You will not get that equation in the exam, but it will be on the formula sheet for you. And the equation tells you that inductive reactance is directly proportional to F and L. 2 pi doesn't change, it's a constant. So what would happen if the frequency increased? Let's look at the answers. Be zero at all frequencies, that's not true. Remain the same at all frequencies, that's not true. If it remained the same at all frequencies, F wouldn't even be in the equation. Decrease as the applied frequency increases? No, it's a direct proportion. If F increases, XL would increase. The inductive reactance would increase as the frequency increases. Inductive reactance is directly proportional to F and L. Question 6.7, and see how this formula is going to be so handy for you, as well as the formula for capacitive reactance, XC equals 1 over 2 pi FC. The inductive reactance of a coil decreases as the applied frequency increases. That's incorrect, because as F increases, XL increases, proportional to the inductance. Well, if the inductance doubles, XL doubles. If the inductance quadruples, XL quadruples, because it's a direct proportion. If L halves, XL halves. So the answer is that inductive reactance is directly proportional to inductance, and it's also, and I'll type this in, and frequency. That's what the equation tells you. Question 6.8. The reactance of an inductor, and I haven't got the formula there for you now, increases as the applied frequency rises. That's true. I don't have to read any further. I'll highlight it now, I'm not sure of it, because XL equals 2 pi FL. And the reactance does increase as the applied frequency increases. In fact, it increases in direct proportion. So if the applied frequency doubles, the inductive reactance doubles. Question 6.9. These coils, or inductors, are all wound with the same type of wire on air cores. So they all have the same core and the same wire. Which coil has the most inductance? Well, the larger the diameter of a coil, an inductor, the more the inductance, and the more turns, the greater the inductance. So it's going to have to be the 28 turn inductor, and it's going to have to be the 28 turn inductor with the biggest diameter. In this case 15 millimeters. 28 turns is going to have more inductance than 28 turns 10 millimeter. It's going to have more inductance than 21 turns 15 millimeter too. So the answer is 15 millimeter, 28 turns. You could get a question similar to that in your assessment. Question 6.10. This diagram, it's a photo, represents what? Well, looking at it, it's got an electromagnet, a coil of wire. So if you pass a current through, if you connect a voltage here, you'll pass a current through the coil of wire. That will pull this armature down. That's a moving armature that will pull downwards. And when that armature, so when we energize the coil, the armature pulls down and the switch operates here. So a small current could be used to switch a much larger current with this device. And of course the device is a relay, and it was also invented by none other than Joseph Henry. He invented the relay for the telegraph because once you ran the telegraph line more than about 10 kilometres, the resistance of the wire became too great. So after about 10k at the top of the pole, they would put a relay and a battery, and that relay and battery would be operated by the line prior to it, and switch in a new battery to boost up the voltage of the Morse code signal. So every few kilometres up a pole you'd find a relay and a battery, which would have to be changed of course, to extend the distance over which the telegraph could operate. Question 6.11. The total inductance between A and B. Well, this is a series circuit, and for a series inductive circuit, the total inductance is given by the equation LT equals L1 plus L2 plus L3. You just add them up the same as resistors in series. So the total inductance of this circuit then is 450 microhenries. So the correct answer is, oops, I've got a C there and I should have a D. Let's fix that up for you. That might not be fixed on the sample question sheet, but I think you know it's supposed to be a D. So inductors in series, same as resistors in series, just add them up to get the total inductance. Question 6.12, the total inductance between A and B. Well, here we've got a series parallel circuit. We've got 350 microhenry inductors in series, and that series combination is in parallel with the 150 microhenry inductor. So we can reduce the series circuit by adding them up. 3 times 150. The series circuit has a total inductance of 150 microhenries. So if you replace these 3 inductors with one inductor of 150 microhenries, you then end up with 150 microhenries in parallel with 150 microhenries. The value of one inductance divided by how many inductors there are, the answer will be 75 microhenries. I hope you understand that. Do the series circuits first by combining the inductors or resistors into one resistor. That leaves you with a parallel circuit only, and because they're the same value, you can divide the value of one inductor by the number of inductors there are, and in this case we get 75 microhenries. Question 6.13, the total inductance between A and B is, we have two 50 millihenry inductors in parallel. When inductors are in parallel and of the same value, you take the value of one inductor, 50 millihenries, and divide it by the number of inductors that there are, and that gives you 25 millihenries. So answer A is the correct answer. Question 6. Excuse me. Question 6.14. The total inductance between A and B is, well, we have a series parallel circuit. We have two 100 microhenry inductors in parallel there. We have another two 100 microhenry inductors in parallel there. So if we worked out the total inductance of the parallel circuits, take the first one, well, they're both the same, they're both two 100 microhenry inductors in parallel. We can simplify that circuit by working out the total inductance of those parallel circuits. 2 into 100 goes 50. So in effect what we've got is 50 microhenries. Oops, typo. So that's the first two 100 microhenries. Then we've got the middle 50 microhenries, and then the last two 100 microhenries also reduce to 50 microhenries. And now it's a series circuit, and we use L2 equals L1 plus L2 plus L3, giving us 150 microhenries for the total inductance of that circuit, which is answer B. Well, that's it for this tutorial. I'll see you again. I hope your course is going well for you. Any problems, please drop me an email to ron@res.net.au or send me a text to my mobile. I'll be quite happy to give you a call if you need some assistance. Cheers for now. See you in the next tutorial.